Heisenberg's uncertainty principle. Good evening. Tonight we will be covering Heisenberg's uncertainty principle. We will proceed through this topic in a careful, methodical, and unhurried fashion, as the subject demands a certain degree of patience, a willingness to sit with ideas as they slowly accumulate into something resembling understanding, and a tolerance for the kind of repetition that is, in fact, the very cornerstone of genuine learning. We will not rush. There's no reason to rush. The material will unfold at precisely the pace it requires, and that pace is by any reasonable measure a slow one. Let us begin at the beginning, which is, as always, the appropriate place to begin. Thrustisnine, Part 1. Historical context and the intellectual climate of the early 20th century. The year is approximately 1925, and the world of physics is in a condition that can only be described as quietly turbulent. Classical mechanics, the grand edifice, constructed over several centuries by Newton and Euler and Lagrange and Hamilton and many others, whose names we will not enumerate this evening because to do so would take considerable time, had served physicists extraordinarily well for describing the motion of macroscopic objects, billiard balls, planets, pendulums, and the like. The equations of classical mechanics were deterministic in a very precise and deeply satisfying sense. Given the initial position and the initial momentum of every particle in a system, one could, in principle, calculate the entire future trajectory of that system with perfect precision. This was the philosophical foundation upon which classical physics rested, and it rested there very comfortably for a very long time. Then came the atom. The study of atomic and subatomic phenomena in the late 19th and early 20th centuries introduced a series of experimental results that classical mechanics simply could not accommodate. The photoelectric effect, which Albert Einstein explained in 1905 by proposing that light consists of discrete packets of energy called photons, each carrying an energy equal to Planck's constant times the frequency of the light, suggested that electromagnetic radiation had a particle-like character. The discrete line spectra of hydrogen and other elements, which Niels Bohr partially explained in 1913, using a model in which electrons occupy specific, allowed orbits around the nucleus, suggested that energy at the atomic scale was quantized. That is, it could take only certain discrete values and not the continuous range of values permitted by classical mechanics. These results, and many others, accumulated into a profound crisis, a slow-moving crisis that unfolded over decades, and was resolved, to the extent that it was resolved, by the development of quantum mechanics in the mid-1920s. Werner Karl Heisenberg was born on the 5th of December, 1891, in Würzburg, Germany. He was a student of Arnold Sommerfeld in Munich, and later of Max Born in Göttingen, and he spent a formative period working with Niels Bohr in Copenhagen. By the age of 23, he had already made significant contributions to atomic physics, and in 1925, at the age of 23, he developed what is known as matrix mechanics, one of the two equivalent mathematical formulations of quantum mechanics that were developed independently during that period, the other being the wave mechanics of Erwin Schrödinger, developed in 1926. Heisenberg's matrix mechanics was published in a landmark paper in July of 1925, and it represented a fundamental departure from classical mechanics in that it dispensed entirely with the notion of electron trajectories and worked instead with matrices representing observable quantities. The uncertainty principle itself was published in a paper by Heisenberg in 1927. The German title of the paper is Über den anschaulichen Inhalt der quantentheoretischen Kinematik und Mechanik, which translates approximately to On the Perceptual Content of Quantum Theoretical Kinematics and Mechanics. The word anschaulich, sometimes translated as perceptual or intuitive or visualizable, is itself philosophically significant, as it refers to Heisenberg's concern with what can actually be observed or visualized in quantum mechanics, as opposed to what the abstract mathematical formalism might suggest. The paper introduced what we now call the uncertainty principle, and it did so in the context of a careful analysis of what it actually means to measure the position and momentum of a quantum particle. Through it is Part 2. The statement of the principle. The Heisenberg uncertainty principle, stated in its most commonly encountered form, says the following. The product of the uncertainty in the position of a particle along a given spatial direction and the uncertainty in the momentum of that particle along the same spatial direction is greater than or equal to the reduced Planck constant divided by 2. In mathematical notation, this is written as follows. Delta x times delta p is greater than or equal to h bar divided by 2. Here, delta x represents the uncertainty in position, delta p represents the uncertainty in momentum, and h bar, which is Planck's constant h divided by 2 pi, is approximately 1.055 times 10 to the negative 34 joule seconds, or equivalently 1.055 times 10 to the negative 34 kilogram meters squared per second. Let us restate this clearly and carefully, because clarity and care are virtues. The uncertainty principle tells us that there is a fundamental, irreducible lower bound on the product of the uncertainties of the position and momentum of a quantum mechanical particle. One cannot simultaneously know with arbitrary precision both the position and the momentum of a particle. If one measures the position of a particle with great precision, that is, if delta x is made very small, then the uncertainty in the momentum delta p must be correspondingly large. Conversely, if one knows the momentum of a particle very precisely, if delta p is very small, then the uncertainty in the position delta x must be correspondingly large. The two uncertainties are inversely related, and their product cannot be reduced below the value h bar divided by 2. This is not a statement about the limitations of our measuring instruments. It is not a statement about the clumsiness of experimenters or the imperfection of laboratory equipment. It is a fundamental statement about the nature of reality at the quantum scale. It is built into the mathematical structure of quantum mechanics itself, and it reflects something deep and irreducible about the physical world. The position and momentum of a quantum particle do not both simultaneously have precise, well-defined values. This is not an epistemological limitation, a limitation on what we can know, but an ontological fact about what exists. The uncertainty is not in our knowledge of the particle's state. The uncertainty is in the particle's state itself. There is, in addition to the position-momentum uncertainty relation, a second and equally important uncertainty relation involving energy and time. This relation states that the product of the uncertainty in the energy of a system and the uncertainty in the time associated with that energy, or more precisely, the duration of the state or process in question, is greater than or equal to h bar divided by 2. In notation, delta E times. Delta T is greater than or equal to h bar divided by 2. This energy-time uncertainty relation has important physical consequences, which we will discuss later in this lecture, but it is worth noting here that the interpretation of delta T in this relation is somewhat more subtle than the interpretation of delta X and delta P in the position-momentum relation, because time in quantum mechanics has the status of a parameter rather than an observable, and the precise meaning of the energy-time uncertainty relation requires some care to state correctly. Consider Part 3. Definitions of uncertainty. Before we can derive the uncertainty principle properly, we need to establish with care what is meant by the term uncertainty in the context of quantum mechanics. In quantum mechanics, the state of a particle is described by a wave function denoted by the Greek letter psi, which is a complex-valued function of position and time. The wave function psi of x and t, evaluated at a particular position x and time t, is a complex number whose absolute value squared gives the probability density for finding the particle at that position at that time. That is, the probability of finding the particle in a small interval dx centered at position x is equal to the absolute value of p psi of x and t squared times dx. The wave function thus encodes all the probabilistic information about the particle's position. Now, for any observable quantity A in quantum mechanics, position, momentum, energy, and so forth, the expectation value of A, which is the average value one would obtain if one measured A many times on identically prepared systems, is denoted by angle brackets around A, that is, angle bracket A, close angle bracket. The uncertainty in A, which we denote delta A, is defined as the square root of the expectation value of the square of A minus the square of the expectation value of A. In mathematical notation, delta A equals the square root of the quantity angle bracket A squared close angle bracket minus angle bracket A close angle bracket squared. This is precisely the standard deviation of the probability distribution of measured values of A. It tells us how spread out the distribution of measurements is around the mean value. A small value of delta A means that measurements of A are tightly clustered around the mean. A large value of delta A means that measurements are widely dispersed. The uncertainty in position, delta x, is therefore the standard deviation of the position distribution. The uncertainty in momentum, delta p, is the standard deviation of the momentum distribution. These are well-defined mathematical quantities that can be computed from the wave function, and the Heisenberg uncertainty principle, it's a statement about the product of these two standard deviations. It is worth dwelling on this definition for a moment, as it is slightly different from the naive notion of uncertainty as simply how well we know something. The uncertainty delta A is a property of the quantum state itself, not of any particular measurement. Even if we have performed no measurements at all, the state of a quantum particle has a definite value of delta x. It is a mathematical property of the wave function, and this value represents a genuine spread in the distribution of possible position measurements, not an ignorance about a pre-existing definite position. Part 4. The mathematical derivation. We now turn to the derivation of the uncertainty principle from the mathematical axioms of quantum mechanics. This derivation, in its most elegant form, relies on a mathematical result known as the Cauchy-Schwarz inequality. Together with the properties of operators in Hilbert space, we will proceed slowly and carefully. In quantum mechanics, every observable is represented by a Hermitian operator acting on the Hilbert space of wave functions. The position of a particle along the x-axis is represented by the operator x hat, which acts on a wave function by simply multiplying it by x. That is, x hat acting on psi of x gives x times psi of x. The momentum along the x-axis is represented by the operator p hat, which in the position representation acts as follows. P hat acting on ei of x gives negative I h bar times the partial derivative of psi with respect to x. Here, I is the imaginary unit, the square root of -1, and h bar is the reduced Planck constant. Now, let us define two new operators in terms of x hat and p hat. Let us define a hat to be x hat minus the expectation value of x, and let us define b hat to be p hat minus the expectation value of p. These operators represent the deviations of position and momentum from their respective mean values. By this definition, the uncertainty in position delta x is equal to the square root of the expectation value of a hat squared, and the uncertainty in momentum delta p is equal to the square root of the expectation value of b hat squared. The Cauchy-Schwarz inequality in the context of Hilbert spaces states the following. For any two vectors, or equivalently, any two state vectors, the magnitude of the inner product of those vectors is less than or equal to the product of their individual norms. If we define a state vector phi equal to a hat acting on psi, and another state vector chi equal to b hat acting on psi, then the Cauchy-Schwarz inequality gives us that the absolute value of the inner product of phi and chi squared is less than or equal to the norm of phi squared times the norm of chi squared. The norm of phi squared is the expectation value of a hat squared, which is delta x squared. The norm of chi squared is the expectation value of b hat squared, which is delta p squared. Therefore, delta x squared times delta p squared is greater than or equal to the absolute value of the inner product of phi and chi squared. Now, the inner product of phi and chi, that is, the integral over all space of psi star times a hat times b hat times psi dx, is a complex number. For any complex number z, the absolute value of z squared is greater than or equal to the square of the imaginary part of z. And the imaginary part of z is equal to z minus z star, all divided by 2i. So we have that the absolute value of the inner product squared is greater than or equal to the square of the imaginary part of the inner product. The imaginary part of the expectation value of a hat times b hat can be written in terms of the commutator of a hat and b hat. The commutator of two operators, written with square brackets, a hat, comma, b hat, close square bracket, is defined as a hat times b hat minus b hat times a hat. The expectation value of a hat times b hat can be written as 1/2 times the expectation value of a hat b hat plus b hat a hat, which is the anti-commutator contribution, plus 1/2 times the expectation value of a hat b hat minus b hat a hat, which is the commutator contribution. The second term, the commutator contribution, is purely imaginary when the operators are Hermitian. Now, the commutator of a hat and b hat is the same as the commutator of x hat and p hat, since the expectation values are constants and constants commute with everything. The fundamental commutator of position and momentum in quantum mechanics, one of the foundational postulates of the theory, is x hat comma p hat, close square bracket equals IH bar. That is, x hat times p hat minus p hat times x hat equals I times h bar. This is often called the canonical commutation relation, and it is in many ways the heart of quantum mechanics. It encodes the non-classical nature of position and momentum as quantum observables. It can be derived from the operator representations we defined above. X hat acting by multiplication and p hat acting by negative IH bar times the derivative by direct computation on a test function. Given the canonical commutation relation, we have that the expectation value of the commutator of a hat and b hat is IH bar. Therefore, the imaginary part of the expectation value of a hat b hat is 1/2 times the expectation value of the commutator, which is 1/2 times IH bar, and the imaginary part of this, that is, the real number we extract from the imaginary part, has absolute value h bar divided by 2. Putting this all together, delta x squared times delta p squared is greater than or equal to the absolute value of the imaginary part of the inner product squared, which is greater than or equal to h bar over 2 squared. Taking the square root of both sides and noting that delta x and delta p are both non-negative quantities, we arrive at the celebrated result. Delta x times delta p is greater than or equal to h bar divided by 2. This is the Heisenberg uncertainty principle derived rigorously from the mathematical structure of quantum mechanics. The derivation, we note, is entirely a mathematical theorem, a consequence of the Cauchy-Schwarz inequality applied to the Hilbert space of quantum states, together with the canonical commutation relation between position and momentum operators. The principle is not an approximation, not a heuristic, not a rule of thumb. It is an exact mathematical inequality that holds for any quantum state whatsoever. Part 5. Physical interpretation. Having derived the uncertainty principle mathematically, let us now consider its physical interpretation in some depth. The physical interpretation is in some ways even more remarkable than the mathematical result, and it rewards careful and unhurried consideration. In classical mechanics, a particle at any given moment has a precise position, a definite point in space, and a precise momentum, a definite velocity, times a definite mass. These two quantities are independent of each other. Knowing one says nothing about the uncertainty in the other. A classical particle has a trajectory, a smooth curve in space parameterized by time, along which it moves in a perfectly deterministic way. The idea that position and momentum might be fundamentally and irreducibly uncertain, not just unknown, but actually indeterminate, would have been entirely alien to the classical worldview. In quantum mechanics, by contrast, the state of particle is described by a wave function. The wave function is spread out over space. It is not localized at a single point, but has some finite width. This spatial spread is precisely what gives rise to the uncertainty in position. A wave function that is very narrowly peaked around a single point has a small delta x. A wave function that is broadly spread over a large region has a large delta x. But here's the crucial and non-obvious point. A wave function that is very narrowly peaked in position space necessarily has a very wide distribution in momentum space, and vice versa. This is a mathematical property of waves known as the Fourier uncertainty principle, and it is intimately related to the Heisenberg uncertainty principle. The momentum space wave function, obtained from the position space wave function by Fourier transform, has a width that is inversely proportional to the width of the position space wave function. A narrow position distribution corresponds to a broad momentum distribution, and a narrow momentum distribution corresponds to a broad position distribution. This is not a consequence of any physical disturbance. It is a purely mathematical property of wave functions and their Fourier transforms. To make this concrete, consider a particle in what is known as a Gaussian wave packet. A wave function whose probability distribution in position is a Gaussian, that is, a bell-shaped curve. The Gaussian is the minimum uncertainty state. It is the state for which the product delta x times delta p takes its minimum possible value of exactly h bar divided by 2. For a Gaussian wave packet, the uncertainty in position times the uncertainty in momentum equals precisely h bar over 2, with no room to spare. All other quantum states satisfy the inequality with a strict greater than sign. Only the Gaussian wave packet saturates the inequality as an equality. If one attempts to localize a particle more and more precisely, to make its position wave function narrower and narrower, the momentum space wave function becomes broader and broader, meaning that a measurement of the particle's momentum becomes less and less predictable. The particle, in a sense, resists being pinned down in both position and momentum simultaneously. This resistance is not due to any physical force or interaction. It is built into the wave-like nature of quantum states. Heisenberg himself, in his original 1927 paper, offered a thought experiment to illustrate the principle. He considered the problem of observing the position of an electron using a gamma-ray microscope. In order to see the electron at all, one must scatter at least one photon off of it. A photon with a very short wavelength, a gamma-ray photon, has a very high momentum given by h divided by the wavelength. When such a photon scatters off the electron, it imparts a large and unpredictable kick to the electron's momentum. A short wavelength photon allows precise localization of the electron's position because the resolution of a microscope is approximately equal to the wavelength of the light used, but it simultaneously disturbs the electron's momentum severely. A long wavelength photon disturbs the electron's momentum less. The kick is smaller, but it also localizes the electron's position less precisely because the resolution is poorer. This is a heuristic argument, not a rigorous derivation, and Heisenberg's original formulation in terms of this disturbance picture has been refined and corrected in subsequent decades. But it captures the essential trade-off between position and momentum resolution in a physically intuitive way. It is important to note, however, that the modern understanding of the uncertainty principle is somewhat different from Heisenberg's original disturbance interpretation. The uncertainty principle is not primarily about the disturbance caused by measurement. It is about the intrinsic statistical spread of outcomes in any ensemble of identically prepared quantum systems. Even before any measurement is made, a quantum state has definite values of delta x and delta p, the standard deviations of the position and momentum distributions, and these satisfy the uncertainty relation. And the principle reflects a feature of quantum states themselves, not of the act of measurement. Part 6. The energy-time uncertainty relation. Let us now turn to the energy-time uncertainty relation, which we stated earlier as delta E times delta T is greater than or equal to h bar divided by 2. As noted, the interpretation of this relation is somewhat more subtle than that of the position-momentum relation. In quantum mechanics, position, momentum, and energy are all observables. They are represented by Hermitian operators, and their uncertainties are defined as standard deviations of the corresponding probability distributions. Time, however, is not an observable in the same sense. Time is a parameter in quantum mechanics, a label for how the wave function evolves, not a Hermitian operator with a spectrum of eigenvalues. Therefore, the energy-time uncertainty relation cannot be derived in exactly the same way as the position-momentum relation. The correct interpretation of delta T in the energy-time uncertainty relation is as the characteristic timescale for the expectation value of some observable to change significantly. More precisely, for any observable q hat, the time rate of change of its expectation value is related to its commutator with the Hamiltonian, the operator representing the total energy. And one can derive a generalized uncertainty relation that involves the energy uncertainty and this characteristic timescale. The result is, as stated, delta E times delta T is greater than or equal to h bars divided by 2. One of the most important applications of the energy-time uncertainty relation is to the lifetime and spectral line width of excited atomic states. An atom in an excited state will eventually decay to its ground state by emitting a photon. If the excited state has a lifetime of tau seconds, meaning the average time before the atom decays is tau, then the energy of the excited state is uncertain by an amount delta E that is approximately equal to h bar divided by tau. This means that the photon emitted in the decay does not have a single precise frequency, but rather a distribution of frequencies with a width delta nu equal to delta E divided by Planck's constant h, which equals 1 divided by 2 pi tau. This broadening of the spectral line is known as natural line width, and it is an intrinsic and irreducible feature of the decay process, not an artifact of experimental imprecision. Longer-lived excited states have narrower natural line widths. Shorter-lived states have broader ones. This is the energy-time uncertainty relation made directly observable in spectroscopic measurements. Part 7. The generalized uncertainty principle. The position-momentum uncertainty relation is a special case of a more general result known as the generalized uncertainty principle. For any two Hermitian operators, A hat and B hat, the product of their respective uncertainties satisfies the following inequality. Delta A times delta B is greater than or equal to 1/2 times the absolute value of the expectation value of the commutator of A hat and B hat, close bracket. In the notation we have been using, delta A times delta B is greater than or equal to 1/2 times the absolute value of the quantity angle bracket A hat, comma B hat, close bracket, close angle bracket. The position-momentum uncertainty relation follows from this by substituting A hat equal to X hat, B hat equal to P hat, and using the canonical commutation relation that the commutator of X hat and P hat equals I times H bar. The right-hand side becomes 1/2 times the absolute value of ICE H bar, which equals H bar divided by 2. Hence, delta X times delta P is greater than or equal to H bar divided by 2. The generalized uncertainty principle tells us that any two observables whose corresponding operators do not commute, that is, whose commutator is non-zero, will satisfy a non-trivial uncertainty relation. Such observables are called incompatible or complementary observables, following the language of Niels Bohr, who was deeply concerned with the concept of complementarity in quantum mechanics. Position and momentum are complementary in this sense. So are the components of angular momentum along different spatial axes. The x component and the y component of angular momentum do not commute with each other, and there is a corresponding uncertainty relation between them. Conversely, if two observables do commute, if their commutator is zero, then in principle both can be measured simultaneously and with arbitrary precision, and there is no uncertainty relation between them. Such observables are called compatible. The position of a particle along the x-axis and the momentum of the same particle along the y-axis commute with each other. Their commutator is zero, and so there is no uncertainty relation between them, and they can both be known precisely at the same time. Hornois, Part 8. Physical consequences and real-world applications. The Heisenberg uncertainty principle has a remarkable range of physical consequences, some of which we will now describe in some detail. These consequences span from the stability of the hydrogen atom to the behavior of white dwarf stars, to the operation of certain precision measurement devices. The stability of the hydrogen atom. One of the early triumphs of the uncertainty principle as a physical argument, though not a rigorous derivation, is its ability to explain why the electron in a hydrogen atom does not simply collapse into the proton. Classically, one might expect an orbiting electron to radiate energy continuously, losing energy and spiraling inward toward the nucleus until it reaches the nucleus and the atom collapses. The uncertainty principle prevents this. If the electron were confined to a very small region near the proton, if its position uncertainty delta x were very small, then its momentum uncertainty delta p would be very large, meaning the electron would have a large kinetic energy. The total energy of the atom, which is kinetic energy plus potential energy, would increase as the electron is confined more and more tightly, because the kinetic energy grows faster than the magnitude of the negative potential energy decreases. The energy is minimized at a certain characteristic size known as the Bohr radius, which is approximately 0.53 times 10 to the negative 10 meters, or about half an angstrom. This is the actual size of the hydrogen atom in its ground state, and the uncertainty principle argument gives a remarkably accurate estimate of it. Let us make this argument slightly more quantitative, though without claiming it to be a rigorous derivation. The electron is confined to a region of size roughly equal to the Bohr radius a0. By the uncertainty principle, its momentum is at least of order h bar divided by a0. Its kinetic energy is of order p squared divided by 2 where m is the electron mass, which equals h bar squared divided by 2 times m times a0 squared. Its potential energy due to the Coulomb attraction to the proton is negative E squared divided by 4p epsilon naught times a0, where E is the electron charge and epsilon naught is the permittivity of free space. Minimizing the total energy with respect to a0 gives the Bohr radius and the ground state energy of hydrogen, both in agreement with the known values. 0-point energy. Related to the stability of the hydrogen atom is the concept of 0-point energy, which is the minimum energy a quantum system can have, even in its ground state at absolute zero temperature. Consider a particle confined in a harmonic potential, a potential well-shaped like a parabola of characteristic frequency omega. Classically, the particle could sit at rest at the bottom of the potential well with 0 kinetic energy and 0 potential energy, giving a total energy of 0. In quantum mechanics, however, the uncertainty principle forbids this. If the particle were at rest at the bottom, its momentum would be precisely 0. Delta p would be 0, but then delta x would be infinite. meaning the particle's position would be completely unknown, which contradicts the assumption that it is at the bottom of the well. The ground state of the harmonic oscillator therefore has a non-zero energy equal to 1/2 times h bar times omega, known as the zero-point energy. This is an exact result of quantum mechanics derivable rigorously from the Schrödinger equation. The zero-point energy is a direct manifestation of the uncertainty principle. Heisenberg, uncertainty, and electron microscopy. In an electron microscope, a beam of electrons is used to image structures with a spatial resolution far below the wavelength of visible light. The resolution of the microscope is approximately equal to the de Broglie wavelength of the electrons, which equals h divided by p, where p is the momentum of the electrons. To achieve very high resolution, one needs electrons with very high momentum, that is, very high energy. This is entirely consistent with the uncertainty principle. Using high momentum electrons means small wavelength and therefore good position resolution, but it also means the electrons carry significant momentum and can impart large impulses to the sample being imaged. The design of electron microscopes must take into account this trade-off: natural line width and spectroscopy. We discussed this application earlier in the context of the energy-time uncertainty relation, but it is worth re-emphasizing here. The natural line width of a spectral line at the intrinsic width of the frequency distribution of photons emitted by an excited atomic state is delta nu, equal to 1 divided by 2 pi times tau, where tau is the lifetime of the excited state. This broadening is irreducible and fundamental. It is distinct from other sources of line broadening, such as Doppler broadening, which arises from the thermal motion of atoms, and which in principle could be reduced by cooling the sample to lower temperature. Natural line width cannot be reduced by any means. It is a consequence of the energy-time uncertainty relation, the Fermi energy and degenerate matter, in systems of many electrons confined to a small volume, such as the electrons in a metal or the electrons in a white dwarf star. The uncertainty principle plays a crucial role in determining the energy of the system. Because electrons are fermions, they obey the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. When many electrons are packed into a small volume, the confinement implies, by the uncertainty principle, that the electrons must have a wide distribution of momenta, and hence a wide distribution of kinetic energies. The electrons fill up a Fermi sea of quantum states up to a maximum energy called the Fermi energy, and the resulting pressure, called the degeneracy pressure, is a direct consequence of the uncertainty principle and the Pauli exclusion principle acting together. It is this degeneracy pressure that supports white dwarf stars against gravitational collapse. In a white dwarf, the electrons are so tightly packed that the uncertainty principle mandates a minimum momentum and hence a minimum kinetic energy, and the resulting pressure is sufficient to balance the inward pull of gravity for stars below a certain mass. The Chandrasekhar limit of approximately 1.4 times the mass of the Sun. Part 9. Misconceptions and clarifications. There are several common misconceptions about the Heisenberg uncertainty principle that are worth addressing in a systematic way, because clarity on these points is important for a proper understanding of the principle. Misconception 1. The uncertainty principle is about the limitations of measurement tools. This is incorrect. The uncertainty principle is not a statement about what our instruments can or cannot measure. It is a statement about the intrinsic properties of quantum states. Even a theoretically perfect, infinitely precise measuring apparatus cannot circumvent the uncertainty principle, because the uncertainty is not in the instrument or in the measurement process, but in the quantum state itself. Misconception 2. Particles have definite positions and momenta. We just don't know them. This would be the point of view of what are called hidden variable theories, in which there are pre-existing definite values for position and momentum that are simply hidden from us. While such theories are logically possible in principle, they're constrained by the Bell inequalities. which were formulated by John Stuart Bell in 1964 and subsequently tested in a long series of experiments culminating in work by Alain Aspect and others. The experimental results are consistent with quantum mechanics and inconsistent with the local, hidden variable theories, suggesting that the uncertainty principle does indeed reflect a genuine ontological indeterminacy rather than merely an epistemological limitation. Misconception 3. The uncertainty principle applies to large macroscopic objects. Technically, the uncertainty principle applies to all quantum objects, including macroscopic ones. However, for macroscopic objects, a baseball for instance, the mass is so large and the relevant length and momentum scales are so enormous compared to h bar that the uncertainty principle places no practical constraint whatsoever on simultaneously knowing the position and momentum. For a baseball of mass 145 grams moving at 40 meters per second, the de Broglie wavelength is h divided by p, which equals 6.63 times 10 to the negative 34 joule seconds divided by 145 times 10 to the negative 3 kilograms times 40 meters per second. This gives approximately 1.1 times 10 to the negative 34 meters, which is fantastically smaller than any physically meaningful length scale. The uncertainty principle is effectively invisible for macroscopic objects. Ton Zeus, Part 10. The principle in the broader context of quantum mechanics, the Heisenberg uncertainty principle occupies a central place in the conceptual structure of quantum mechanics, and it is connected to several of the other foundational features of the theory. The principle is intimately connected with the wave-particle duality of quantum objects. A quantum particle is neither a classical particle nor a classical wave, but something that has aspects of both. When we speak of the momentum of a quantum particle, we are invoking the de Broglie relation that connects momentum to wavelength, p equals h divided by lambda. A state with a precise momentum is a plane wave, a wave extending through all of space with a definite wavelength. Such a state has a completely indefinite position. The particle could be anywhere in space with equal probability. Conversely, a state with a precise position, a so-called position eigenstate, is a delta function concentrated at a single point, and its Fourier transforms a flat distribution over all possible momenta, meaning the momentum is completely uncertain. The wave-particle duality and the uncertainty principle are two facets of the same underlying mathematical reality. The principle is also connected to the measurement problem in quantum mechanics, the deep and still not entirely resolved question of what happens when a quantum measurement is performed, and what it means for a quantum system to have or not have a definite value for an observable. The uncertainty principle tells us that certain pairs of observables cannot simultaneously have definite values in any quantum state. When we perform a measurement of, say, the position of a particle, the wave function collapses, in the standard Copenhagen interpretation, to a state with a definite position. But this simultaneously ensures that the momentum becomes completely indefinite. The measurement of one quantity disturbs the conjugate quantity, not because of any physical disturbance caused by the measurement apparatus, but because the act of preparing a state with a definite position is, by the mathematics of Fourier transforms and the uncertainty principle, necessarily the act of preparing a state with an indefinite momentum. Das ist Dur, Part 11. Summary and review of key results. Let us summarize, with appropriate care and at appropriate length, the key results of this evening's lecture. The Heisenberg uncertainty principle, published by Werner Heisenberg in 1927, states that the product of the uncertainty in position and the uncertainty in momentum of a quantum particle is greater than or equal to h bar divided by 2. That is, delta x times delta p is greater than or equal to h bar divided by 2. Here,